Hello everyone, I'm Hyunbin Lee from University of Illinois at Urbana-Champaign. Today I'm presenting DOVE, a Data-Oblivious Virtual Environment. This work is done with my collaborator Tushar Joyce at Johns Hopkins, Professor Chris Fletcher, and my advisor Professor Carl Gunter at UIUC. Consider a following scenario where data scientists from UIUC and Johns Hopkins each owns a genomic private data set, and they want to compute a genomic function f on it, where R is the result output from this function. Computation is done in R, a high-level programming language that, as R provides convenient user experience for statistical analysis. But who will run the function? In this scenario, universities cannot disclose sensitive information to each other, so running the function on one of two entities' machines is not a feasible option. An alternative is to designate a third-party cloud service provider that universities can outsource computation to. We will study security of outsourcing scientific computation problem in this presentation. To start off, let's discuss trusted execution environment, TEE, a solution that many propose for this problem. For this talk, we'll use Intel SGX as an implementation of TEE implementation. Intel SGX provides a secure region of execution environment named an enclave. When the function runs inside the enclave, high-level privilege code such as OS or hypervisor cannot directly introspect or tamper the computation on sensitive data. SGX simulates a trusted third party that computes for two parties. Unfortunately, running code under SGX is not as easy as we just discussed. Programmers may adapt their code base to use SGX primitives, as SGX SDKs are currently provided for a limited set of languages such as C or C++. However, this is burdensome for scientists who typically do not know C. Alternatively, researchers developed frameworks that run a library OS in enclaves to support running unmodified binaries like high-level language interpreters inside the enclave. For this model, Intel SGX protects against adversaries who directly monitor memory states, but it cannot stop microarchitectural side channels, the family of attacks that infer secrets of computation by reading microarchitectural states against unmodified binaries. We denote muarch for microarchitecture. Following is a seed code snippet that is intrinsically vulnerable against a variety of side channels. We denote x1 and x2 as private values, and the code simply branches on x1 logical and x2 to assign the value of y. When we visualize possible computation traces of this code, we realize that the code will take a different path depending on the value of x1 and x2, so that indirectly observing the computation trace by measuring timing, cache hits and misses, or other relevant channels enables inference of secret values. Fortunately, programmers have come up with a holistic approach to fix the code. First, using bitwise AND instead of logical AND prevents serial evaluation of x1 and x2, since in C, bitwise AND operator is a gate operator that behaves the same regardless of the inputs. Second, we can simply remove the branch by assigning result of expression directly to y. As a result, the computation trace stays the same regardless of the inputs. This is data obliviousness. The idea of data oblivious computation is to ensure that a program execution exhibits the same observable characteristics regardless of the inputs provided. Different communities have different terms for this. For example, some may call this constant time programming. Regardless of their name, the goal is to provide a software-based solution against side channels. Now, let's come back to our outsourcing computation problem. How can we protect ourselves against side channels for high-level languages, such as R, with data-oblivious computation in mind? Recall that we provide secret inputs I1 and I2 to an R interpreter that runs R script F. This interpreter runs on a library OS inside the SGX enclave. Hence, in order to run the script data obliviously, we need to ensure that the whole programming stack, ranging from the R script written by data scientists to library OS inside SGX, to be written data obliviously. Unfortunately, this is not a scalable solution. For example, our interpreter alone has 1 million lines of code. What can go wrong if our interpreter is not written data obliviously? We'll use the aforementioned expression x1 and x2 written as an example. Note that this expression was data oblivious when written in C. Our interpreter is mostly written in C such that most R functions have its implementations written in C. Unfortunately, this single AND operator is implemented with nested if statements in the interpreter as shown on the right. This is due to the fact that R has the notion of not applicable and a nullisk value that requires edge case handlings for most R functions. As a result, the computation done on R's single AND operator becomes similar to that of C's double AND operator. The expression that seems data oblivious in C is not data oblivious in R. Depending on the value of the operands, the number of instruction counts differ, which suggests a side channel vulnerability. We found numerous cases like this throughout the R codebase, suggesting infeasibility of ad hoc fixes for every data-dependent code segment. We introduced Dove, a solution for security and privacy of outsourcing scientific computation that targets high-level programming languages, supports for existing code against aforementioned microarchitectural side channels without requiring a trust that the application code is written data obliviously. We will use R for our case study. The key insight of our approach is that data obliviousness implies data unnecessary. Some may ask, what do you mean by data unnecessary? Assume we have a data oblivious function f. Input I1 result in result R1. By the definition of data obliviousness, the function will always produce the same execution trace regardless of the input I1 value. So what we do is to replace actual data I1 with stand-ins of the data. We call these stand-ins as pseudonyms. They are not actual data, but they share the same public attributes, such as dimensions and bit length with the input. Running function f without I1 will not result in useful result output, but will result in an execution trace that is the same as that of original input. If we replay that execution trace on a real data set, then we should produce the same result R1. What we accomplished is a separation of script evaluation with actual operations on sensitive data. There are several benefits to this separation. First, the function f without actual data cannot run data-dependent primitives. How can the function run a branch on secret input predicate when the function does not know what the secret is? Instead, the function should perform data-oblivious transformations to those primitives, such that the resulting execution trace is data-oblivious. We call this trace a data-oblivious transcript. Second, we can easily contain the code that runs the data from other complex layers, such as language parsing and evaluation. We ensure that the code that replaces the data-oblivious transcript or dot is only composed of data-oblivious primitives such that this runtime becomes our only TCB needed to block microarchitectural side channels. We introduce our Dove design, which is composed of 3 components. The first is front-end that runs user's R script with pseudonyms to generate a dot counterpart. The dot, analogous to intermediate language representation in other languages, conforms to a set of grammar rules so that the resulting transcript becomes a data-oblivious counterpart of original R script. This dot and private datasets are sent to a Dove backend, which is a small SGX enclave application consisted of data-oblivious primitives. The backend parses and checks the dot and runs dot on datasets and gets the result. Our backend prototype is small, around 7K lines of code, as we implement a subset of R base functions in a data-oblivious fashion. Nonetheless, those functions were suffice to implement most of our benchmark genomic scripts. Front-end can run on client's local machine outside of Enclave. The front end runs an R script on pseudonyms and generates a dot so that it converts the R function's operations in base R, a default library functions that we chose to implement on the backend to dot semantics. As a result, the dot contains all functions operated on pseudonyms. Here is a short R code snippet that defines a pseudonym matrix X and runs a statistical function summation on the pseudonym. The front end transforms the code into the dot, the straight line code counterpart of the original program. In this example, summation function runs on pseudonym matrix X that is represented as $1 in dot to produce a pseudonym matrix scalable variable %1. Note that an operation's operands are pseudonym, then the result is also a pseudonym. What to include in the dot grammar greatly affects security performance trade-off for our system. Current dot grammar is consisted of functions that we chose from our base functions, the functions that are required to define an object-oriented programming for R. These range from simple addition to statistical functions like summation. Note that control flow constructs like if and for that is innately data dependent when used with pseudonyms are included in our implementation. The R dot grammar must disallow these traditional control flow constructs, but it supports predicated execution and bounded iteration loops as alternatives such that front-end transforms these control flow constructs to aforementioned data-oblivious counterparts during the transcription process. For full details on dot grammar, please refer to our paper. Finally, Dove backend receives dot and dataset. This is the TCB against SGX Enclave. The job of the backend is to first load and parse the dataset and dot to ensure that the dot complies previously mentioned grammar rules. The dot is then run on datasets and the result is outputted. For security analysis of Dove, we focus on this step, since all prior steps from dot generation and front end to dot parsing do not touch sensitive data at all. Our security analysis is made with static code opcode analysis that analyzes object dump files of C and C++ files for our SGX application, and dynamic trace analysis done with Intel PCM. For full details of our security analysis, please refer to our paper for full details. To summarize, Dove is comprised of the three components: front end that transcribes original R script, dot, a straight line code counterpart of R script, and the backend that parses and runs the dot. We evaluate expressibility and performance of Dove with a family of benchmark R scripts used in the wild. We utilize Honeybee dataset for our performance evaluation. The dataset was used in actual market party scientific study by a crop scientists in UIUC. We successfully run majority of benchmark scripts without requiring any modification to original R code. This suggests our Dove grammar is expressive enough to cover a variety of use cases. When running benchmarks, we compare performance of Dove with SGX against vanilla R without SGX to capture the runtime overhead of Dove. The overhead is comprised of three parts. The green bar is the overhead incurred due to data-oblivious transformation. Blue is the overhead due to running constant time fixed point library against floating point side channels. And sky blue is the overhead caused by running backend inside the enclave. In conclusion, we introduced Dove, the solution that targets security and privacy of outsourcing scientific computation for high-level languages, supporting for existing code against aforementioned microarchitectural side channels without requiring a trust that the application code is written data obliviously. Thank you.